Great, thank you. Most of you probably know, Annalisa is going to talk about meltwater and sub-mesoscale variability in the Labrador Sea. We've got another webinar coming up in January. Yukon and Kushner is going to talk about North Atlantic response to atmospheric forcing with and without ocean dynamics. So mark that one down on your calendar. Okay, go ahead, Annalisa.
Hi, good morning, everybody. I prepared a talk for 45 minutes, and I figured out this morning I had to cut it down. So I'm going to mostly give you an overview of a work that we have done and was really led by Renato Castellaro, UGA, and Hao Luo, that worked partly in my group and partly in Renato's group, looking at what happened in terms of meltwater from Greenland and the impacts of that meltwater, which is growing significantly on the circulation. And then I will move on some more recent results about what that means in terms of sub-mesoscales, but this is really very much still work in progress. And this is really part of an investigation of what is needed to properly model Labrador Sea convection. And this is motivated by the fact that the CMIP5 models have been showing consistent large bias in the representation of the Labrador Sea mean state, and that has a large impact also on the representation of carbon and oxygen storage in the deep water. This is just to remind you what the Labrador Sea looks like. It's a basin that has a large amount of internal variability. Deep convection can be very strong and very weak, and we had decades of both. It's a relatively well-known or well-studied basin because we do have decent data coverage since the 1960s, and it's kind of a unique situation in terms of convective basins. Let me see, then I forget how to change. It's a very localized convection. What I'm showing here, it's a modeling results, but match the observation extremely well, and is mixed layer depth average in a simulation that was 30-year long, and that had a very good representation of interannual variability between February, March, and April, or May, June, and July. And what you can see is really the location of deep convection in the late winter and early spring. And the localization it's due to heat fluxes, and it's essentially linked to the topography over land and over Canada, and where cold air essentially comes through. It's not linked, for example, to sea ice positioning. What we've been working on for a while at this point has been a model. We use ROMs that in regional configuration 4, so the boundary by reanalysis, especially we use SODA. We have done also an extensive comparison of different reanalyses to find out what would work better, is able to reproduce the internal variability quite well, but also the intraseasonal one. What you see here is a comparison of the model convective activity versus the observed, and you have data from Argo in the plot to the right, and data mostly from single annual cruises on the left, and we have subsampled the model exactly like the observations for that comparison. And what you see at the bottom is the time series of mean temperature between 150 and 2,000 meters for the model and for the observations from 1950 onward, and that shows the how the model reproduced the interannual changes. So this is just to give you an idea of the instruments we have in hand. What we are doing right now, it's extending the investigation to the whole North Atlantic and really trying to figure out what is the minimal resolution, for example, that is needed, where the errors in CMIP5 are becoming really critical. So it's that in terms of boundary conditions on the ocean side, or is that in terms of heat fluxes, for example, from the atmosphere. This figure shows that we're also doing a very good job in terms of seasonal cycle representation. This is something that the models have really, the CME5 models have really big problems in reproducing. Well, it can be captured with a regional one. And this is true for both weak convective years, and in that it's the comparison with the Argo data, or with strong convective years, and those are data, a comparison with a compilation of data that Fiamma put together in 2006. So we have this instrument that is working pretty well. We have done an investigation, first of all, to determine what is really driving the deep convection. This was published in 2016. And on top of that, we wanted to see what the impact was of the meltwater, which is one of the conditions that are changing the fastest in this basin. So the first thing I want to just show you here, it's a correlation between heat fluxes and convection. Just focus on the two columns to the right. And we divided the years from the 1980 onward in strong convective years in blue, or weak convective years in red. And if you focus on the top right, what you can see is that in strong convective years, most of the convection is explained, the strength of the convection, the intensity of the convection is explained by the strength of the heat fluxes. There is a very strong correlation between the two. In weak convective years, it does remain strongly statistically significant, but definitely decrease. And a contribution comes from the changes in the Irminger current that also became warmer, and therefore through the eddies and the eddy variability brought warmer water in the convective area. The third ingredient, once you have more or less assessed what is going on in terms of heat fluxes and Irminger current, is the meltwater component. What we are doing right now, on a more general terms, is really to explore the whole region shown in this plot with nested regional simulations of various resolution in the area indicated by the box, by the darker box. So we ran at 15 kilometers the whole domain, and then at 1, 2.5, 5, and 15 kilometers for the Labrador Sea. But what I'm going to describe more in details are really simulation done at 2.5 kilometers, where we are including the freshwater fluxes from the meltwater from Greenland. And this is essentially the domain we're focusing on. And the reason for this, it's that there has been a very large, substantial increase in meltwater from Greenland in the past 10 years or so. Here we are, it was definitely lower before 2005. Here we are showing the period from 2008 to 2012. And the interesting component is that the meltwater that has increased the most is the one on the western side, while on the eastern side of Greenland, the meltwater has been more or less constant over this period. It's higher than it was before 2005, but has been more or less constant through the 2008 to 2012 and even 2013 years. We have estimates of the meltwater for 108 ice sheet catchments. Those are derived also from satellites data. And what we have done is to implement pretty much the model that I showed you before, at 2.5 kilometer, adding the meltwater on both East and West Greenland. And we have been running from 1999, and I will be considering mostly the period 2008 and 2012. Looking specifically at where the meltwater go and what are the implications of this input of fresh water for the convective area that, as we saw before, it's about here. Okay, so we have to get that meltwater in the convective area to see if that may change the stratification in that area. This is a model validation. At 2.5 kilometers, the model is doing really surprisingly well. It reproduces the potential temperature, again, in the convective area extremely well over the whole period, and as also very good representation of surface salinity. Surface salinity, we don't have tons of data, but considering what we have, we are really representing the seasonal cycle of that, and the mean. The mean is at the top, the seasonal cycle is at the bottom, quite well with the model. And this is including the 108 fjords and catchments for the ice sheet. What can be seen in the model using tracers is that there is a lot of interannual variability in how much water, meltwater, comes into the convective area, and especially which kind of meltwater gets into the convective area. What I'm showing here are two cases, 2008 and 2012. In 2012, there was the largest in the period considered discharge of meltwater from West Greenland. And in 2008, there was one of the minimum years for the West Greenland component. The East Greenland, as we mentioned before, it's pretty much similar to the whole period, across the period. And another thing to notice, well, the first thing to notice in this figure, looking at those figures, is that it's pretty clear that the meltwater from West Greenland does not really arrive into the convective area in any of those years. And this is true for the whole period considered, really. The one that managed to get into the convective region is the one from East Greenland. And the other thing to notice is that if you look at the lines that we put in the bottom left figure, there is really not much meltwater across this area painted with magenta lines. And it's much more the meltwater, the freshwater that is coming from East Greenland that is able to get into that region, which is more than 200 kilometers from the coast, and eventually propagate into the rest of the North Labrador Sea and all the way around into the convection zone. This is quantified in the figure shown here, where you see the volume of meltwater that arrives in the box that is here in black. Okay, so the volume of meltwater that gets there, it's definitely small for the one that comes from West Greenland. It's much higher for the one that comes from East Greenland. And then at the bottom, the two figures at the bottom represent the percentage of all the meltwater from each side getting into that area inside the black box. And what you see there is that, again, for the West Greenland meltwater, there is never more than 20% that arrives at essentially starts at 25% at 100 and something kilometers, and really at 200 kilometers, there is always less than 20%. While in the East Greenland component, it's the one that up to 60% of what is melted can get in in that area identified in the previous figure by the black box, and then essentially by those bands. And so here it's really giving us a kilometer from the coast. The other thing to notice is that there is a very large interannual variability, and this is seen, like for example, 2012, that was the largest discharge from West Greenland. It's the one that has the least impact, and where the meltwater essentially does not get outside the coast more than in all other years. And 2008 or 2009, there was not particularly exceptional years. It's where indeed you had the largest freshwater amount getting offshore. So the reason for that, it's that the transport and the advection of the meltwater, it's essentially controlled by the winds. And the relationship between the winds and the meltwater for at least the East Greenland component can be seen in this slide. When you have downwelling winds, so essentially the cumulative wind stress is negative, you are essentially simply transporting the water north along the coast, and you are not bringing it offshore. And you really need to have the upwelling component to be able to bring the water further offshore. There are years where the upwelling, the winds are downwelling most of the time. Sorry, it's here. And there are years where the winds behave. They are mostly downwelling in the summer, but they turn in the upwelling. They have an upwelling contribution in fall, and that becomes important for the East Greenland contribution, because it takes about 60 days for the water from East Greenland, a minimum of 60 days, 2 to 3 months really, to get into the region interest by Irminger rings, essentially. And so that time, by the time you have the fresh water along the coast, so you are actually in a situation where the winds are dominantly upwelling and transporting the water offshore. Also in years where that is not possible for the component that is coming from West Greenland. And that's especially true for 2011, where the upwelling winds really picked up in fall, and so you can see a large contribution from the East Greenland freshwater, but you don't get the same for the West Greenland part. Lastly, we have done an experiment where the contribution of the meltwater was doubled compared to today's value, and essentially rerun for the same years, but with twice as much fresh water and twice as much melting. And the salinity anomalies are indicated in red for the new runs, while in blue it's for what has been obtained in the realistic scenario. And what is shown in the bottom figure, it's the mixed layer depth anomaly that you will have when you double the melting in the convective regions. So you end up with possibly as much as 10 meters anomaly in mixed layer depth in the fall, late fall, early winter, whenever you double the melting, which is what is expected by the end of this century. So in summary, only about 1 to 15%, depending on the year, of the surface meltwater runoff from southwest Greenland is transported westward, while there is about 50 to 60% of the runoff that originates from southeast Greenland that is transported westward. If you double the meltwater, as predicted for future climate scenarios. You get more than doubles of the anomaly transported offshore that persist into winter. And the interannual variability in such transport is strongly linked to the wind forcing. And just to quickly conclude, what we are now doing is also look at what it's the impact of those freshwater anomalies on the representation of the sub-mesoscale circulation. And to do that, we are considering even higher horizontal resolution. We are down to 1 kilometer. And we are focusing on 2008 and 2012. And I just want to give you an idea of what the simulation looks like. This is Filippo Taglis that has been running them. Here you can see the vorticity distribution in 2012, with and without riverine forcing, meltwater really more than riverine. That's me with the wrong title. But you can really see the difference in vorticity. And so what we would like to quantify is what that difference means in terms of offshore transport and mixed layer depth in the area. And just given I'm running out of time, for 2008 we don't have yet the simulation without the rivers. But this is a seasonal cycle of sub-mesoscale variability, essentially, of vorticity. But when you have high normalized vorticity on average in the region, it means that you have a lot of sub-mesoscale variability, because that's what gives you high values of normalized vorticity. Just look at the green and orange lines. Those are 6-hourly outputs. And what you can see is a seasonal cycle that shows a very strong peak in some mesoscale activity in summer, which is opposite to what happens in open ocean, because it's impacted by the melting and the meltwater fluxes. And this is calculated 200 kilometers from the coast. So it's coast, all the regions up to 200 kilometers from the West Greenland area. And this is where we are, and we're trying to figure out what are the impacts of those sub-mesoscale circulations on the propagation of the on the representation of the propagation of the freshwater anomalies into the domain, and how they change depending on the wind conditions.